Right now, with all political and social reality that we face, this hunger of energy is tremendous. On the left side, energy is produced in large amounts, not needed at this geographical location. But you see on the right side, metropolitan conglomerates where you have a high demand of energy. The challenge is how you get the energy from left to right. Siemens Energy is making sure that the energy flows in this world, produced and transported, stored, and make available where we need it. Whenever we want to start our home appliances, whenever we are in an industrial area and we need to make sure that our production line is powered on and working, this is where we come into play and make sure that the energy is available. Transporting big amount of energy over long routes is not possible in classical technological ways. What we need is high voltage direct current technology. So we provide 2 transmission stations. We convert the energy into direct current, transport it, make it flow, and on the other side, we transform the energy back again. Projects were exchanging data in the past using Excel sheets per discipline. It is a great tool to gather your own data inside your own discipline. But when it comes to exchange the data, make the data updated whenever it changes at one end, Excel doesn't perform that well. What we wanted to do is to not get rid of Excel as an idea, but to merely take this concept of a spreadsheet and define a technological layer on top of that enables us to centralize those spreadsheets. And this is the moment our tool, Plant Asset Manager, was created.
Good morning, everybody. Now, for today, my first question to you would have been, how many of you have ever heard about Siemens Energy? But you know what? Looking at the stock markets lately, I think the better question would be, how many of you already own Siemens Energy stocks? Hands up. Oh, quite a few. So this is not the professional financial advice, but yeah, you know what I have to do. Siemens Energy is not Siemens anymore. Siemens Energy became a few years ago a separate company with its own mission and vision and doing in the business field quite well. 11 years ago, as we were still part of Siemens, we started a digital transformation. A transformation that was affecting not only our IT landscape, but it led also to a mindset and culture change. It affected also our own internal engineering processes. And of course, here, Qt played a very important role in this transformation. Siemens Energy's mission is to energize society. We cover all areas where energy is produced, is transmitted, and is needed. But we set the focus on the industrial field. My team and I, we are in the energy transmission business. For you to understand, this is the place where electrical highways are being constructed. We deliver to our customers, each of our customers, we deliver turnkey solutions. They are tailored solutions based on their own needs. Now, the solutions that we deliver are complex, as you might see here. The engineering process of such solutions typically takes a few years to complete, and there are a few hundreds of people involved in this process. Now, the energy hunger of the past years put a tremendous pressure on the way we are doing engineering. Moving from the past order intake of projects from 4 to 6 per year, today we have a 20 plus projects order intake rate. So you can imagine we have a big scalability problem. You probably heard about this cobbler's children syndrome. This is this old tale where the cobbler's children go without shoes because the cobbler is busy making shoes for everybody else. Now, in analogy at Siemens Energy, we experience the same. We are busy in delivering outstanding solutions to our customers, but we forget about our own well-being as a developers or engineers. In terms of tools, methods, processes. But what does it mean exactly in our domain? The IT landscape complexity that we are using, the tools that are we using, is that the whole complexity is increasing. Keeping adding cognitive load to our engineers. You have to keep in mind, our colleagues in engineering, they are not software developers, not IT savvy people. They are electrical engineers. So, as you might see here on the bottom line, you have the IT landscape, which is ever-changing in a dynamic and constant evolution. And we have on the top side the engineering teams, the business domain that needs a stable IT environment, right? In order to maximize their productivity. So what we came up with, we decided to fill this gap, to introduce an engineering platform layer in between that talks on one side the language of the engineers, and on the bottom side integrates seamlessly with the IT landscape and makes place and embrace the changes. It's like an anti-corruption layer between those two levels. The main components that you see here, just a quick glimpse. We have an engineering portal, which is a cloud application. You have here authentication, authorization, user management. You have here configuration management and delivery management, covering also some cybersecurity topics. We maintain our own cloud environment. So we are not concurrency to AWS, but we use AWS in order to make it fit for our engineering domain. We have our own observability framework because we don't want to go blind, implementing the DevOps principles. We need transparency, monitorability, etc. We design our own CI/CD pipelining frameworks in order to be rolled out into the projects. And last but not least, we have our own data backbone, representing the whole information in terms of parameters and configurations needed in the project. We try to make this layer as thin as possible and reuse and use existing horizontal IT solutions available.
Yeah, I think if you look at that middle layer, it might look very familiar to you if you've ever set up infrastructure for a large distributed, multi-functional, cross-functional software development project or team. And I think that's actually a key point to make here. Dacian realized very quickly that these projects actually look an awful lot like very large software projects, and then therefore the tooling that we use as software engineers through these sorts of complex projects might be helpful in engineering a transmission system. We'll go a little bit more into that.
Exactly. So we might say using everything that is available on the software world in the engineering area would solve our problems, right? Yeah. Well, actually, it's not that easy. The challenge that we faced is the way the project teams were dealing with data and information. Here you can see in an example, we have one piece of equipment. This is the transformer that we deliver. And we have on the bottom line all the disciplines or the silos that are interested into maintaining data for these ones. And what we see here is that each and every discipline has a tendency to reap their own part of data that they need from the actual equipment take it into their own silo, maintain it, and never caring about designing the data structure with others. Everybody has the ability and the power to define their own data models in their own spreadsheets, maintain them. They can even do UI engineering, nice colors and interaction, and build logic into that. So what we needed to do is to come up with a set of requirements that were meant to tackle these problems. We needed to centralize the whole data. That was the first thing that we looked for. We separated between data providers and data consumers, needing to allow the data consumers to define their own data interfaces and to own them. Be the owners of those data interfaces, and the data providers then just needed a place to know the place where those data interfaces are and to put the data in a very intuitive manner. We also needed a way to be able to exchange data towards other tools, like here the 3D models. But not only to that, we need to export, in terms of reports, data to our customers or to our suppliers. And of course, we needed to be able to run sanity checks on that data, and also, since we were there, to have some key insights reports. On the internal side, means to filter the data, search the data, identify what is there, what is not there. Two key topics here were, whatever we choose as a technology for this centralized thing, it needed to be also available offline, because sometimes we do commissioning on the sea on these platforms where you don't have any connectivity to the outer world. And we needed to support the whole process lifecycle, for tendering up to commissioning and operation. To summarize still here, if you look at our engineering domain, but you can imagine and abstract any kind of domain, you have your objects, you have your assets, equipments, and you can look at those equipments from different perspectives. There are multiple ways to look at them, from mechanical perspective, from electrical perspective, how noisy they are, how damaging they are for the environment, chemical compounds. What we needed to do is to find a way to digitalize all this information, all these views, put them into some kind of a database, create some structures that should be pretty stable, and make this information very easily accessible. So for us was the moment where we created our plant data digital twin of the whole plant. Here in this case, we had the data modeling problem, and on the other side, we had the tooling problem. What kind of tooling we had to choose. Today, this talk, we will focus on the tooling part. The data modeling topic will be a topic for another talk. If you look on the left side, you have a piece of equipment. This is called disconnector. This is what you know from your room is the lighting switch. In our domain, this lighting switch looks a little bit more complex. It's something like the monster from Stranger Things, but nevertheless fulfills the same functionality. And in the middle, you see a snapshot from our tool. We came with the concept of an asset being an object that has the potential to represent any kind of objects in any kind of domain. And we have the concept of aspects, where we group data together that needs to stay together. And we store everything on file share. It's that simple, in open text formats. At the end, this is how the application looks like. On the left side, you see a workspace tree containing all the assets together that are relevant to be put in this plant. And in the middle, you see a table, the data container that is being stored in a plain text as a JSON format, can have a schema embedded or can use as a remote schema definition, has a scripting interface, and you can even assign the user actions. Well, that's not all till, but I think we have time for yes.
All right, so as I said, this looks an awful lot like a software project, doesn't it? And that's not an accident. Basically, the key idea is that a lot of the tooling that we already have, like for example, Git for centralized and offline capable version control. Yeah. So in practice, just in case you're curious and you want to build something similar to this, maybe in your domain, it uses GitLab sort of as the central piece of technology here. And then basically tools that interface with GitLab in various ways. And PAM, Plant Asset Manager, which is the Qt-based rich client, if you will, basically interfaces with GitLab in a variety of ways. We're dealing with very large amounts of data here that are changed very frequently. So that requires a bit of engineering to get the performance right, caching, and so on. But offline capabilities are really important, as Dashan mentioned. Notification of changes, because people work on this concurrently, just like in software development, and you want to know when somebody from another domain changed the definition of something or changed an asset in a particular way. So there's notifications, and again, Git is really helpful, and GitLab is really helpful in terms of tooling for getting that done.
Having Git here,
it was the central decision that we took years ago. It was key enabler for the adoption of this solution and the success in the organization. It was actually really a love it or hate it story. Not using a classical database management system in the first place was a very conscious decision that it took, because we needed to have electrical engineers be able to interact with this data, to evolve, let them evolve data structures on themselves, and not, build a separate IT department with software developers that only they can work on that. So this enabled us to get started fast, enabled us to unify engineering and development workflows, because, hey, since you have Git, you have all kind of workflows that you can take if you want Git flows and apply them. So actually we treat information and data and configuration as source code. It's exactly the same. Our documents written in a plain text format that needs to go through the same changing steps that a normal source code does.
So for technology, it's, as I said, a Qt-based desktop application. It's Git as the storage and transport layer. It's CI/CD downstream, and then you do have web-based access to some of the data, because you don't want, that's the downside of having a rich client, that you need to install it. So from a deployment point of view, there are more casual use cases where it makes more sense to have web-based access that doesn't require installation of an application. So those do exist as well. But at the core of it is a Qt desktop application.
Yeah, obviously it worked for us, but nothing comes 100% free. There are also downsides to this approach, like in terms of performance, tackling, dealing with a lot of files on Windows systems especially is a pay in performance, implementing our own Git client on top of that. But hey, somewhere our developers also need to have fun, right? So
I'll do it again. Would you get it again?
I would do it again, or at least I would use the same disruptive thinking that we had back then. But definitely I would do some research, contemporary research on what is available today. Now, coming back to Qt, we love Qt. Qt was, before we started with this project, our weapon of choice in terms of developing desktop applications. For us, it's a delight in C++. We inspire ourselves from the Qt implementation itself. It is a mature framework, as we saw yesterday. Excellent performance out of the box, cross-platform. Hiring the right set of skills brings us tremendous gain in productivity. And this is what also worked very well for us. Well, in terms of, developing a desktop application with the widget technologies, there are the downsides here are merely in the lack of out-of-the-box available widgets that provide more functionality that we have right now in the standard in the Qt toolbox. Like, everybody loves Excel in our domain. They need the same functionality also in our application, or that demand that. We need things like sorting, filtering, and so on. Yeah, and having said that, we have not said everything and enough, but the time is up. So if you want to know more, please visit the Keynote booth. Here you can see a short glimpse of what is still possible, also possible with our application, how to build or use
object-oriented concepts in order to evolve and build asset structures. Here you can see both of us are extending are in the role of the CCO of KDAP and software architect of Siemens Energy, which respectively are KDAP and Siemens employee. And Phil, we can only say, the two assets of us can only say,
Thank you very much.
thank you very much for your attention.